Okay, so guys, so I want us to carry on with the idea of linking the derivative that we've seen with the integration that we showed in previous videos. So we arrive at this symbol here, which is the difference between 2 points in the function and 2 points in another variable. Let's say delta t, could be time, could be anything, and we loosely made a connection between the derivative for which I didn't give the exact definition. I will give it in a moment. But when the steps are very small, we can write this as a ratio. And we also know that this depends on the point where you calculated it, because we know that if we are dealing with a curve, for example, the derivative, which is a small straight line represented, for example, here, um, here, here, and here, the steepness of this line is dependent on the point where you calculated it. So this can be thought as a function of time, and sometimes is written f prime dt, but this is just notation, so that's not to be fuzzy about it. So I said that I want to give the formal definition. The formal definition involves a limit that I'm not going to talk about at the moment, but I will just give a rough idea of what it means. So you take a point of the function and then you make a difference, as we said. So this is not very far from what we saw so far, because our definition so far was this one, okay, which is very close to what I'm writing here. Okay, as you can see, there is a limit, meaning that this difference on the top and the bottom, and as you can see, t can cancel out, but it's the same as two different points in time, t plus h and t. So we can say just this, okay? And these are two different points in time. We do the difference, and the steps goes to 0, as you can see. So this means that our step, which is h, is actually going to 0, which means that we are refining our derivative very tiny, with very tiny steps, many tiny steps. Okay, so this is the formal definition of derivative, at least in one dimension. Okay, where is the connection with the integral that I want to make? So first of all, let me write it down here on one more time. We can play with the definition, and I will convince you that this is correct. I will stick with my rough definition of derivative to make the loose connection with the integral. I will give the link for the theorem that states this correctly, but for the moment we are happy with this. So as you can see, I'm just playing with the elements of this equation, because this is in blue, this is our derivative, okay, and then as you can see, if you in yellow, if you bring this guy down here, which you can't because it's different from 0, and you bring this guy back on the other side, changing the sign because you're subtracting it, we get the same equation. Which is this one, right? So with two simple passages, division and subtraction, we can write this in full. But this has a nice interpretation, because if you look at it, it means that you, in some sense, okay, to make my life easy, I will pick the t1 point equal to 0, as in our curve starts from 0. We don't have to do that always. There is a way to handle with this, but let's make my life easy. So t1 is 0, f is 0, because in the graph we start from 0. So this can cancel out, this can cancel out, and this can cancel. No, but let's, yes, and this can cancel out. Okay, so as you can see, we can write the function is very easy now that I removed everything. But basically, we can reconstruct the function at any point by considering the derivative and the step that you take in the horizontal axis. Now, if you remember the integration that we saw in the last video of a function of x, okay, this integration was loosely connected with a sum of many terms, as many as we want, and xi plus 1 and then xi plus 1 minus xi. This was the definition that we've got from previous slides of the integral. So there is a sum and there is a step and there is a function. So we are close to this, right? Because as our f function here, that can be written f dt, can be thought as if you want, you can think about this in many. Let me see if I can do it correctly. I need no, but let me rewrite. It's easier if I rewrite with the sorry about the confusion. Let me put back the t1. It helps. It will be 0, but for the moment I need it in the equation to make the easy connection. Otherwise I got confused. T2 minus T1, okay, and then the F0, FT1, sorry, which will be F0 in the end, I will bring it here, minus F1, FT1. Okay, so exactly, so we have a difference of 2 points, and we have this position here. But if you keep summing differences of 2 points, so for example, let's call this f t of n because we are refining our steps, and then this is f of tn minus 1, and then we sum the next, which is f tn minus 1 plus f tn minus 2, etc., up to ft0. We see that all of this contribution here, which we keep sum together, they have some cancellations. So this cancel out with this cancel out with the one on top, and only the two extremes remains. So we can actually say that the initial point and the final point, the difference of the initial point and the final point of our curve, which are in this case fn because we chopped it in many pieces, ft0, can be written as a sum of many of these contributions here on top. And this is basically, let's write this ratio as a new function, gdt I plus 1, and this is ti plus 1 minus ti. So you see that we are actually computing an integration, because the connection is in red is this one that I want to make, and then I can write easily the integral of the derivative of f in dt between t0 and t1. This is the connection that I want to make. Okay, so in a sense we are led to the conclusion that if we want to calculate, so we can reconstruct the function with the derivative. As you can see, the derivative is here. Namely, we integrated the derivative and we can retrieve our function in any point. And we need to remember where we start from. It can be 0, it can be anything, but we need to remember where we start from. So, okay, this is a fundamental theorem of calculus. I will link it at the end of the slides. But let me do one more thing, which I guess can be fun, maybe not fun, but at least useful. I don't know. I like it, so I will do it. So let me erase this one. It takes a bit. there was a bunch of stuff. I could change the size of the eraser, but if I do that, I'm sure I will close the presentation. I have to restart again for the third time, and I'm a bit annoyed by redoing it the third time. So let me be patient. Sorry, be patient. I wish I had the music on to alleviate the pain. Okay, good. So what I want to say is do some examples of derivative. So we know, and using some nice formulas from algebra. So we know that derivative of x in dx is equal to 1, and this is because x1, x2 minus x1 divided by x2 minus x1, these cancel out, and this is 1 in every point. So the derivative of a line is a constant, and it's 1. We know that. Fantastic. Then we know that derivative of x squared, we calculated that before. We do the calculation again. Square, this is just a rough derivative, but the thing carries on with the limiting procedure in these simple cases. It can be proven quite easily. So this is equal to, if we remember the formula, a squared minus b squared, which I will link it to a minus b plus a times, okay, a minus b plus a times b. So this is x2 minus x1 plus x2 minus x1 plus, sorry, this cancel out the denominator. We have 2 points which are summed together, but since they are very close, we can say they are the same point x. There are 2 of them, so we have 2x. Okay, so here I'm thinking of x2 roughly equals to x1, which will make it equal to 1 because we are chopping the function in very small pieces. So we have the derivative of x2 of x squared, sorry, is 2 times x. And you can see this time is not a constant, it's not 1, it's not the same everywhere, it changes wherever you are in the graph, as you should. Now, we can do a step further easily, the cube, and then I will try to extrapolate for larger. So at cube, we need to do, the step would be cube minus x1 cube. Sorry, this is a cube, I will change it in a sec. Okay, and for this one, we need to remember a nice formula, which we can prove easily, but I think I'll link it as well, which is a squared plus ab plus b squared. Okay, so we can prove it easily. A times a squared is a cube, ab squared goes away with minus b a b squared, and minus b times b cube is b cube. So okay, so this formula works, and we can plug it in here, and of course we have x2 minus x1 minus x1 in the denominator times x squared 2 plus, oops, there is no space, so let me, okay, these two cancel out, we can cancel those two, which is easy, and the only thing that remains are the 3 terms, x2 squared, x1, x2 plus x1 squared. Okay, those 3 things are the same when we apply the same idea that x2 is very close to x1, which we call it x. So x cube derivative boils down to 3 times x squared. Okay, as we just see, x squared. Okay, now I want to give you, so what this leads to, that a general formula for the powers, for all the powers of n, when n is at least integer, that says, this by the way will be useful in future videos when I will talk about power series and how to approximate a function with polynomials. So it's good to know these formulas now. And this can be written as n x n minus 1. Okay, so this is the formula that is general, and but I want to, so what I want to do is I would like to give you an idea of why this is true for large n, for any n. If I can do it, I will do it quite quickly using, I think I'm using correctly. I hope I'm doing it. Otherwise, you can correct me or comment it in the at the end of the video. I want to use the induction idea. So demonstration by induction. So when you say that something is correct for some integer, a formula is correct for an integer n, and then you prove that if it's correct for n, it's correct also for n plus 1, and then you prove that it's correct for any n. So the idea is that we know that that works for x2, x3, and whatever. Now we need to prove that it works, that if it works for xn, it will work for x to the n plus 1 as well, so the step forward. And this means that we are inducing the idea that it will work for any bigger n as well. So how do we go about it? So first of all, we write the general, so we forget about this in a moment, we know that we are dealing with that. So we assume that this is correct, and we write xn minus x1n divided by x2 minus x1. Okay, now this can be written as x2 minus x1, and now we'll try to convince you that this is correct. At least I will do my best. So this is a bit, it's not a very nice notation, but let's see if I can convince you that this is correct. Okay, so what this change symbol means. So we saw that this is the case for x squared, because there is x minus y, x plus y. Okay, so 2 is here, and this is the same, this sum with less term. So there is no wacky multiplication terms. But when we do the cube version of it, we know that that starts to look a bit like this, because we have these two squares, which are these ones, and then there is one term, only one, because it goes up to 1, the sum of a multiplication of x and y, which is this term here. And then if we do with 4, and then I will stop doing it, because otherwise I'm doing all the calculation. It's not good. So this can be written as x cubed, sorry, and then x cubed, I think it's like this. Okay, if we do the calculation, this should be okay. There will remain only these terms, and we see that these are the two terms that are appearing in this term, in this sum, in the blue square, and then there are the extreme, which are these two as well. So what I'm saying is that we can assume that there will be a sum of terms, and the important thing that that we need to remember is that the sum will be such that I times j, so the powers of the two elements in the product, will be basically n plus 1 in this case, and the sum goes from k that goes from 1 to n, which is one step less than the maximum exponent, which is n plus 1. So with these two things in mind, I should be able to convince you that this formula here will be will allow us to make the formula with n plus 1 true. And how do we go about it? So we do one step further. We multiply the left side by n, okay, and plus 1, okay, and then we keep this way because it's there, and we multiply by x plus 1, and then we keep this formula n plus 1 plus x1 n plus 1 plus this weird sum with all the component that have these properties. Okay, now this will leads to 4 terms. One is x2 n plus 1, which is what we want, x1 n plus 1, which is what we want, and 2 extra terms, which is x2 n plus 1 n minus x1, so this is a minus and this is a plus, x1 x2 n, which if you see, they are of the kind present in the sum here, so we will deal with them later on. But so we keep this one aside, and then we multiply oh, sorry, I made a mistake. This was clearly n minus 1, not n plus 1, and this is n minus 2. Yes, otherwise I'm foolish. Sorry about that. Okay, now it's correct. Of course, because we are removing stuff. So this is n minus 1, and this is n minus 2. And now it works. Okay, so what happens is that now we multiply these terms down here, this one inside, and we get x2n plus x1n, and then some other terms of the same kind of this sum. And how many we are adding them? We are adding 2, but we are subtracting 2. So actually we are adding 1 and 2. Yes, we are adding 2. So it goes up to n. And then we subtract one term, which is from the other side, and it goes up to n minus 1, k1 of this strange ij k sum here. But what I want to say is that basically this formula, I will give the explicit formula which I cannot retrieve at the moment, right, in the link. But the idea is the following. Basically, we are basically saying that we use the fact that the formula was good for x to the n, and then we are inducing the idea that it works for n to the n plus 1. Now we of course we want to bring this on the other side, x2 minus x1, because we wanted to do the derivative. Remember, we want to do the derivative of xn plus 1 of dx. So this is the point of the derivative, the rough derivative. And how many terms there are here? There are n terms. Okay, so we do the same approximation that x2 is equal to x1 roughly, which is equal to x. So this means that we have n plus 1 terms, x2 to the n. Okay, so this is kind of leading to the idea that the formula that we drew at the beginning, that was delta xn divided by x, which is x n minus 1, also works for n plus 1. So we are safe to say, since it works also for n2 or n3 or n4, whatever, that this formula is correct. And we can use it later on. So as a finishing remark, I want just to show you how to use this formula to simplify the calculus of some integrals, and I will do it just for x squared, for which the summation is a bit tricky. It's nice to do, but it's a little tricky. So maybe we can, if you're interested, we can show I can show the details of the summation up to a certain point at least, with some approximations. But let's see if this connection that we made between integration and derivatives can help. So suppose we want to integrate the f, and we know that we know this because we show it. Okay, but this is the value, the initial point of the formula of our integration. So we know that if we take the derivative, we can, and we integrate it, we can reconstruct the function. So what do we do with x squared? So we can do the sum, or we can remember that the derivative of x cubed divided of x is exactly 3 times x cubed, as we saw before. So what is missing here is that the integral of f, if we look at this formula, we want to have the derivative inside. So we put a 3 x squared in the x, okay? Because this is the derivative, but this is not x, this is 3 times x cubed, okay? So we divide it by 3 because we have x, only x here, and we have 1/3 x 3 exactly. So the integration of x squared then there is another nice formula, it's x cubed divided by 3, and we can, instead of doing the summation of x squared minus x1 to I plus 1 I divided by xi plus 1 minus xi times xi plus 1 minus x1. So you should carry on all this summation and then refining with the limit and then see what happens. So we can use this instead to calculate at least the easy derivative of the powers quite quickly. And also there is a constant that is always the initial point that we can, for example, pick to 0 in this case, but it doesn't matter. So yes, so with that I'm finishing, I'm concluding. So we made a connection with the integration, we conclude the idea of derivatives, and hopefully this will give you an idea on how to use them on very basic functions that are still very useful for many applications, as we will see. So good, have a good day and see you next time. Ciao.